Welcome to the lecture covering 5.2, Power and Polynomial Functions. All right, let's get going. Get my pen here. A power function is a function with a monomial term that is the product of a real number, a coefficient, and a variable raised to a fixed real number. In other words, with a power function, the variable is not going to live as the exponent. The exponent will be a fixed number. So we have just the general form of a power function here. So K is the coefficient, X is the variable, and P is that fixed real number that the variable is raised to. So we are asked to choose which of the following functions are power functions. The constant, let's look at these. So the first one we have here is the constant function. There's an understood x raised to the 0 power here. And since 0 is a fixed number, although you don't see it, the constant function is a power function. F of x equals x, the identity function, that is also raised to a fixed real number, understood 1. Quadratic function raised to a fixed number 2. X cubed raised to a fixed number 3 there. Our power functions, we tend to consider that fixed real number as a positive value. So let's take a look at these other 4 toolkit functions. Okay, so the other toolkit functions here, we have the reciprocal function, which we know from our exponent rules, if we bring that x up to the numerator, that will become x to the negative first power. And since raising x to the negative first power is raising it to a fixed value, this is also considered a power function. Same thing for reciprocal square. This is the same thing as x to the negative 2. And then we have the square root of x. That can be rewritten as x to the 1/2 power, also a power function. And the cube root of x is x to the 1/3, also known as a power function. So now hopefully we have a better understanding of what this statement means when it says anytime you have a variable raised to a fixed real number, then you are dealing with a power function. Okay, so we will talk in the next section, which is also the next test material, about specific types of power functions that we group into under the heading of polynomial functions. And that is where we limit ourselves to that fixed real number that the variable is raised to being a positive integer. But for just our power functions here, anything raised to that fixed real number is considered a power function. So which down here are power functions? this first one is because if I multiply those factors together, I get 8x to the 4th. So it fits the description of a power function. Here, I cannot combine my x to the 5th term and my x cubed term, so I have negative x to the 5th plus 5x cubed. And because I have more than one term, I am not a monomial. This is not a power function here. And then finally, because I have more than one expression being raised to different powers, this would not fit the bill either as a power function. So this one's not either. Okay, so we can identify what we call the end behavior of power functions. And this is just how the tail ends of a graph are expected to behave based on the power, the value of the power that the variable is raised to. So you can either have that variable being even or odd, I'm sorry, not the variable, the power being even or odd. And then you can also have the coefficient on that term being positive or negative. So other books I've taught out of have called the test on the function to determine its end behavior the leading coefficient test, but it's actually not the leading coefficient. It is the sign of the leading coefficient. So the sign of the leading coefficient and the even or oddness of the power itself. So I would always call this the leading term test. Your book doesn't name it, and that's okay. So if the power is even, let's look at this first column. If your power is even and your leading coefficient is positive, the tail ends of your function are both going to be pointing upward. I call this tails up. And one example of this type of function is the quadratic. So f of x equals x squared. It's a big U opening up. I believe this is probably an x to the 4th that we're looking at here because of how wide it is. But x squared is a nice example that we can keep in our head of a positive even term there. And then we also have an even-powered negative term. And that has both tail ends pointing downward, so tails down. And a simple example of that, f of x is equal to negative x squared. We know that having that leading coefficient negative causes the x squared to reflect over the x-axis. And if the power is odd, if our leading coefficient is positive, we have You can call this falls left, rises right. And the most basic one of that is just the line. So this is falls left, rises right. So the identity function f of x equals x, something that looks like this, that's an example of a positive odd. You can see that the left side goes into negative infinity in its y values or its range, and the right side goes into positive infinity. And then finally we have negative odd. And this rises left and falls right. And that would be, the most basic is just negative x. And the reason that is considered raised to an odd power, let me remind you of this, both of these are raised to the understood first power there. Sorry I didn't point that out earlier. But we have rises left, falls right. So negative x would look like this. We can see that rises left and falls right. Okay, so that's all you have to know is the sign and the even or oddness of that monomial term. Or we'll find out next chapter in the case of a polynomial function, it's the leading term. Okay, so given your power function f of x equals k times x raised to the nth power, where n is a non-negative integer, identify the end behavior. In other words, we're not talking about rational functions here where n can be negative. And it's an integer, so we're also not talking about roots, because we know that we get roots when we raise to a rational or fractional exponent. All right, so with this first one, we have f of x is equal to x to the 8th. This is considered positive because the leading coefficient is understood to be positive 1. So this is a positive even because 8, so 1 is my positiveness, and n equals 8. Actually, I should say k equals 1 there, and n equals 8. So this is a positive even. So I should think of the positive quadratic, and this is going to be tails up. Now, that is not the mathematical way to describe this. How we describe this mathematically says, as my domain approaches negative infinity, what's happening with my range? Well, f of x in both of these cases approaches positive infinity. As x approaches positive infinity, f of x also approaches positive infinity. That says tails up. And that's how you're going to have to write it, by the way. All right, let's take a look at this next one. F of x equals negative x to the 9th. This would be considered a negative odd. It's negative because k is understood to be negative 1, and it's odd because n is 9. So I can think of the negative line, and that would be rises left, falls right. If I want to write that mathematically, as x approaches negative infinity, f of x approaches positive infinity. That's rising left. As x approaches positive infinity, f of x approaches negative infinity. That falls right. All right, and finally, for this concept, we have a negative even because k is -5 and n is 4. So this is going to be a tails down, just like the negative quadratic. And how we say this mathematically is as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x still approaches negative infinity. Okay, so a general note about polynomial functions. Now we're expanding this idea. We're going to touch on what a polynomial function is here, but then on the next test and in the next section that we study, we will break down polynomial functions in a lot greater detail. Okay, so let n be a non-negative integer. So once again, we're limiting ourselves to that degree being a positive integer. A polynomial function is a function that can be written in the form of a sub n times x raised to the nth power plus ... a sub 1 times x raised to the understood first power . Oh, they have a typo here. Interesting. Okay, so let me fix their typo. This should be a sub 3 x cubed, because I'm talking about the standard form here for a polynomial function, all the way down a sub 2 x squared, a sub 1 x raised to the understood first power, and a sub 0, and there's an understood x to the 0 power there, which we know is just 1, so it doesn't show up. Okay, so this definition looks super scary here, but it's really not. The n's in the very first leading term there, those are just standing for the degree of the polynomial. N is equal to the degree of the polynomial. So the a sub n's are standing for the coefficients, and they're going to correspond with whatever power that particular term is being raised to. And since we want a general definition for a polynomial, we could have a polynomial that's raised to the 57th power. So the way we say that, so that it covers anything, is a sub n times x to the nth power. So a sub n is the coefficient that goes with the degreed term. So a sub n specifically will always be your leading coefficient. And we don't know how many terms we're going to have because we're trying to give a general definition. That's what the ... dots are for. So if I start at the 57th degree, I've got to work my way down a sub 56, x to the 56th, a sub 55, x to the 55th. So that's why they put the ... dots there, because you're going to go all the way down until you get a sub 3. That's going to be on my, this right here, a sub 3, That is the coefficient, the general name for the coefficient on the x cubed term. That's why it's a sub 3. So the n's and the values that you're seeing there are just naming systems. These don't actually have a value at this point. This is just a general theoretical definition of a polynomial. So hopefully that demystified everything for you. All right, so the questions down at the bottom, which of the following are polynomial functions? Well, because I can multiply these terms together and get 6x to the 4th plus 4, this is considered a polynomial function. Now, you're not seeing all of the terms that actually exist. If I expanded this out, in this case, before I get started, my a sub n would be equal to 6, and my n is equal to 4, because it's a 4th degree polynomial. But if I expanded it out to see all of the terms that could potentially be there, I would have 6x to the 4th plus 0x cubed plus 0x squares plus 0x to the understood first plus 4. So in this case, a sub 0 is equal to the constant 4. A sub 0 is always your constant term tacked on to the end. So yes, this is a polynomial function. And this next one, if I distribute, I end up getting negative x cubed plus 4x fits the definition of the polynomial function. In this case, a sub n is equal to negative 1, n is 3, and a sub 0 is equal to 0. Because remember, a sub 0 is always your constant term. Well, there's not a constant term that you see there, but it's understood to be there. So this is a polynomial function. Now, this last one, I could rewrite it as 5 times x plus 2 raised to the 1/2 power. Since that factor is raised to the 1/2 power, it is not an integer, which means this is not a polynomial function. You see here, n has to be a non-negative integer to be considered a polynomial function. Now, it is a power function, but it's not a polynomial function. This is the same idea that functions are subcategories of relations. So polynomial functions are subcategories, or are a subcategory of power functions. Okay, so just showing you more about that definition there. I've already gone over that. Given a polynomial function, identify the degree and leading coefficient. So to do that, you're going to find the highest power of x to determine the degree. Identify the term containing the highest power of x to get the leading term. And then you're going to identify that coefficient to know what the leading term is, or the leading coefficient is. Okay, so identify the degree, which is n, the leading term, a sub n, and I'm sorry, a sub n is the leading coefficient. The degree is n, and the leading term is the entire term. So, the leading term here is negative 4x cubed, which means that n is 3 and a sub n is -4. So you always have to identify the highest power to know which one is the degreed term. So the leading term for g of t is -2t cubed. So n is also 3, and a sub n here is -2. And then finally, my leading term is -p cubed. So n is also 3 here, and a sub n is understood to be -1. Okay, so identify the degree, leading term, same thing down here. So my leading term is -x to the 6th, which means my n is 6, and my a sub n is understood to be -1. Okay, identifying end behavior of a polynomial function. Knowing the degree of the polynomial is useful in helping us predict its end behavior. Same thing we just talked about. There's no difference here. But instead of just having a monomial to look at, now you're going to use the leading term to identify end behavior. Because the power of the leading term is the highest, that term will grow significantly faster than the other terms as x gets very, very large or very, very small. So its behavior will dominate the graph. For any polynomial, the end behavior of the polynomial will match the end behavior of the power function that is associated with that polynomial function as its leading term. So here, we know we had to have had a positive odd. It is positive odd because it follows the same end behavior as our most basic positive odd, which is a positive linear function. And that is falls left, rises right. To say that mathematically, as, okay, to say that mathematically, as x approaches -infinity, f of x approaches -infinity. As x approaches positive infinity, f of x also approaches positive infinity. And here on the right, we have a negative even. It follows the same tail end behaviors as our negative quadratic. And to say that mathematically, we say as x approaches -infinity, f of x approaches -infinity. As x approaches positive infinity, f of x approaches -infinity. So tails down there. Okay, given the function -3x squared times x minus 1 times x plus 4 expresses the polynomial in general form. Determine the leading term, the degree, and the end behavior of the function. Okay, so the good news is you don't have to multiply this all the way out. But what you do have to multiply is what would make up the first term, so the leading term. And what's going to make up that leading term is this first monomial factor being multiplied by the leading term of each of the other binomial factors. So my leading term is going to be -3x squared times x times x. My leading term is -3x to the 4th. This leaves me with a degree of 4. And since this is a negative even, I should expect tails down. And I'm not going to write that out in words again, but it would say as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches negative infinity. All right. So if we multiplied all of our first terms there, we would end up with a leading term of 0.2 x cubed. My n is 3, and my n behavior is determined by that leading term. It is a positive odd, same thing as my line. Falls left, rises right. Okay, identifying local behavior. So we also have turning points that show up in these graphs that are very important. Other important points are the x-intercepts and the y-intercept. All right, so a turning point of a graph is a point at which the graph changes direction from increasing to decreasing or vice versa. So it's a high point or a low point. It's a local maximum or a local minimum. The y-intercept is where it crosses the y-axis. Don't forget, a y-intercept is going to have an x value of 0 or an input value of 0. Just the opposite for x-intercepts. X-intercepts are going to have y values or output values of 0. How do you determine the intercepts? You literally plug in 0 for the opposite one than what you're looking for. So if you're looking for an x-intercept, you're going to plug in 0 for f of x or y. And if you're looking for a y-intercept, you're going to plug in 0 for x. So given this polynomial, determine the x and y intercepts. The y-intercept is the easiest one to find, so we'll do that first here. And to find a y-intercept, I just plug in 0. Or let me label this. This is the y-intercept. So I'm going to plug in 0 for x. So f of 0 is 0 to the 4th minus 4 times 0 squared minus 45. That's 0 plus 0 minus 45, and that's just negative 45. So here's a hint. Your y-intercept will always equal a sub 0, your constant that's tacked onto the end, because everything else is going to get zeroed out, because every other term is going to have a variable in it where you're going to plug in 0, and it's going to zero that term out when you multiply with it. Now, the x-intercepts are a little trickier. You have to do some factoring. So I have to plug in 0 for y or f of x here. So I have 0 equals x to the 4th minus 4x squared minus 45. So I can use substitution to make this a quadratic. We'll say that u is equal to x squared. So if I rewrite my function using substitution, u squared minus 4u minus 45. And then I can use the AC method to factor this because I want to factor and use the zero product property. I could use the quadratic formula as well, but I'll factor it. It's factorable, so I believe it's factorable. Yes. So A times C, 1 times negative 45 equals negative 45. And I'm looking for what multiplies to make negative 45 but adds to make negative 4. And that is negative 9 and positive 5. I rewrite. So I have 0 equals u squared minus 9u plus 5u minus 45. Now I divide and conquer, so split it down the center. Here I can take a u out, and I'm left with u minus 9. The other two terms, I can divide out a positive 5. Remember, you always want to put your sign on that second set. And this leaves me with u minus 9. This is still equal to 0. So I find out that 0 is equal to u minus 9 times u plus 5. And so my zero product property says, well, if that's true, then either u minus 9 had to equal 0, or u plus 5 had to equal 0. Here u is 9. Here u is negative 5. U is equal to x squared. So x squared is 9. X squared is negative 5. I can use the square root property to solve. And here I get x is equal to positive or negative 3. Remember, I can square positive 3 or I can square negative 3. And here, x squared is equal to the square root of negative 5i. That means x is equal to the positive or negative I times the square root of 5. Those are imaginary solutions, and we've already learned those do not show up on the graph. All right, so let me show you that with this particular polynomial function, which I'm writing it down here, f of x is equal to x to the 4th minus 4x squared minus 45. They didn't ask us to do this, but it does not hurt before we go and look at this graph to try to identify the end behavior. My leading term is x to the 4th, so that means that this thing is a positive even. I should expect to see tails up. I have a y-intercept at negative 45, and I have two x-intercepts at positive and negative 3. So let's go take a look at the graph of this function just to verify everything. Now, we won't do this with all of them, but I think it's important to at least look at one of them. Okay, so if I go to my graphing calculator, and I have x to the 4th minus 4x squared minus 45. Let me zoom out so you can see. There we go. All right, so notice tails up. I have a y-intercept at, see if I can get it to register there. Oops. Not. Okay, there we go. Negative 45. And I have an x-intercept at negative 3, 0 and positive 3, 0. Notice I do not have an x-intercept of positive negative I square root 5. Because remember, the imaginary zeros do not show up on the graph of the polynomial function. We learned that when we were studying the quadratic function. Now, we were not asked to find these, but we also have two minima, and that is at negative 1.414 and an x value of positive 1.414. The actual minimum value is negative 49 for this function. Okay, let's go back to our whiteboard. Okay, so same type of question, different polynomial function to deal with. So the first thing we want to find is the y-intercept by plugging in 0 for x. F of 0 equal to 2 times 0 cubed minus 6 times 0 squared minus 20 times 0. 0 plus 0 plus 0. Notice I do not have an a sub 0 that shows up, so it's understood to be 0. And the x-intercept, this is what I get when I plug in 0 for y, or f of x. 0 equals 2x cubed minus 6x squared minus 20x. I can begin to whittle this down with factoring by factoring a GCF of 2x out, and that leaves me with x squared minus 3x minus 10. I'm not going to go through the whole process of factoring using the AC method for the sake of time, because I can do this one in my head, and I just showed you an example of factoring with the AC method. So this is equal to 2x times x minus 5 times x plus 2. Now I can use my zero product property to solve. So I have 2x equals 0, x minus 5 equals 0, x plus 2 equals 0. Here we divide both sides by 2 and we get x equals 0. Here we add 5, so x is 5, subtract 2, x is negative 2. So I have one y-intercept. It would not be a function if it had more than one y-intercept. I have a y-intercept of 0, and I have 3 x-intercepts, 0, 5, and negative 2. Just talking about the end behavior that is determined from the leading term. So in this case, this is a positive odd, going to have the same end behavior as a positive sloped line. Okay. A polynomial function has no breaks in its graph. In other words, the graph can be drawn in its entirety without lifting your pen from the paper or pencil. It's a smooth curve with no sharp corners. And a sharp corner is like the absolute value function. That comes to a sharp point. The turning points of a smooth graph must always occur at rounded curves. The graph of polynomial functions are both continuous and smooth. So these are the characteristics of all polynomial functions. Turning points. So the tops of the hills or the bottoms of the valleys where you're changing from increasing to decreasing or decreasing to increasing. We can know how many of those to expect because a polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. So, without graphing the function here, determine the local behavior of the function by finding the maximum number of x-intercepts and turning points. So the max number of x-intercepts that this thing can have is n. My n here is 10, so I have a maximum number of x-intercepts. Now, it doesn't have to have 10. It just can't have any more than 10. And it has turning points, also call those points of inflection, n minus 1, which is 10 minus 1 in this case, or 9, at most. At most. It does not have to have 9, but it can't have more than 9 turning points with being a 10th degree polynomial. Okay, same thing here. So my x-intercept at most n. Now you got to be careful because sometimes they'll give these polynomial functions to you not in standard form, so you need to identify that leading term, the one with the highest exponent. N is 12, so I'm going to have at most 12 x-intercepts, and I will have at most n minus 1 or 12 minus 1 or 11 turning points. Okay, so we're given these two graphs here, and it says, okay, what can you conclude about these just from the way their graph looks? We can conclude that it has x-intercepts. It looks like these are the point negative 2.5 and 0, and positive 2.5 and 0. Which means those came from linear factors, x plus 2.5 times x minus 2.5. So that's where those x-intercepts came from, because I had to use the zero product property to find that positive 2.5 and that negative 2.5. I have got, looks like, 3 turning points. 1, 2, 3. So since I have 3 turning points, that means that that 3 had to be equal to n minus 1. So when I add 1 to both sides, that means my n or my degree had to be 4 there. So this is a 4th degree polynomial. It's positive. It's a positive. The reason I know it's positive, tails are up. With 3 turning points, so the degree had to have been at least 4. And, yep, I've got 2 x-intercepts, so I have at most 4 x-intercepts, but in this case I've only got 2. All right, this next one, I have 3 x-intercepts, 2 turning points, and rises left, falls right. So since I rise left and fall right, this had to be a negative odd. And specifically, I have 3 x-intercepts, which means my degree is 3 because I have 2 turning points. So n minus 1 had to equal 2. If I add 1 to n, had to be 3. There we go. Last slide. Okay, given the function, okay, so without looking, determine the local behavior. Well, I need to find out what that leading term is. The leading term is negative 4x cubed. So this is a negative odd, which means rises left, falls right. My n is 3. N minus 1 is 3 minus 1, which is 2. So I have 2 turning points. Same thing here. I'm going to multiply it out. My leading term would be 0.2 x cubed. That is a positive odd. Falls left, rises right. My n is 3, and n minus 1 is 3 minus 1. This is also going to have 2 or fewer turning points. And this last exercise, for the following exercise, you use the information about the graph of a polynomial function to determine its function. Assume the leading coefficient is 1 or -1. There may be more than one correct answer. Okay, so I have a y-intercept of 0, 0. In other words, my a sub 0 is going to equal 0. You're not going to see just a constant tacked onto the end. My intercepts are 0, 0, and 2, 0, my x-intercepts. Those had to come from x minus 0 and x minus 2. Well, we wouldn't write x minus 0. We'd write x times x minus 2. This gives us a quadratic because x times x is x squared. However, we're told the degree is 3. So I need to add another x term there that would come out as a 0 when I apply the zero product property. The end behavior says as x approaches negative infinity, so here's our little graph, as x approaches negative infinity, f of x approaches negative infinity, so that's this way. As x approaches positive infinity, f of x approaches positive infinity. So I'm going to have an understood positive 1. You're not going to write it in there. Understood positive 1 a sub n, or leading coefficient. So to answer this, one possible function would be x squared times x minus 2. That's all I have for you. I hope this was helpful.